Hello. Today we start with the combinational logic. We show the source from which we have taken the slides. Before we go in detail on the combinational logic, we would like to inform you that there are two types of digital circuits. One is the combinational digital circuits, which consists of logic gates, and therefore the outputs of the circuit are determined only from the present combination of the inputs. And the operation of such circuits can be specified by sets of Boolean functions. The other type of circuits is called sequential digital circuits, which employs, in addition to the logic gates, it employs storage elements, which means it has memory also inside the circuit. The outputs of these circuits are function of both the inputs to the circuit as well as the state of the storage element, which means the output will also be affected by what is stored in the memory elements that are included in the circuit. Therefore, the outputs of the sequential circuits depend on the current inputs as well as all past inputs. Usually we say that these circuits have feedback connections. This is a block diagram or a black box to what we call combinational circuit, and this circuit has n inputs on the left hand side and m outputs on the right hand side. We know that n inputs have 2 to the n possible combinations for the values. This means if we have only 2 inputs, there are 4 combinations, which are 0, 0, 0, 1, 1, 0, and 1, 1. If we have 3 inputs, we have 8 combinations, and so forth. Each circuit usually performs a specific function. As an example, it can perform the function of addition, so it can add 2 numbers, A and B, and give the result, the sum, as the output, or it can subtract 2 numbers, or it can compare 2 numbers to give us whether A is greater than B, or equal to B, or less than B, or they can act as a decoder, or encoder, or multiplexer, and we will explain all these later on in this chapter. These circuits are usually of what we call MSI, or medium scale integration circuits, and we usually also call them standard cells, because if we have an adder, from this adder we can build larger adders. Same applies for decoders, encoders, and so on. Before we design a combinational circuit, first we talk about the analysis of the circuit. Again, before we start analyzing the circuit, we have to make sure that it is combinational rather than sequential. Combinational means it has no feedback path. In order to analyze the circuit, we either derive the Boolean function or write down the truth table of the circuit. Why do we do analysis? We use analysis as one way to verify the design of a circuit. Or we can provide verbal explanation of the function of the circuit after we find out the Boolean functions. Let us give an example. If we are given this circuit where it has 2 inputs, X and Y, and 1 output, F we call it, with 4 NAND gates. Now, looking at the circuit, what is the function of the circuit? Of course, we cannot know the answer unless we perform analysis to the circuit. To do the analysis, there are 3 steps that we follow. First, we label all the gate outputs with symbols. Second, we find the Boolean functions for all the gates. And finally, we express the functions in terms of the input variables and simplify. For the example that we have just seen for this circuit, as an example, we name the output of the first gate we call it T1, T for temporary, which equals XY prime. And then we also call the output of the second gate T2, which is X multiplied by or ANDed by T1 prime. And then the other gate, we call it T3, which is Y T1 prime. And then finally, the output of the last gate is F, which equals T2 and T3 prime. In order to find F now, we would like to write down the value of F equals T2 and T3. So we substitute T2 is XT1 prime dot YT1 prime prime, and when we employ De Morgan's law, we get XT1 plus YT1, and this is equal to X and XY prime, or Y and XY prime. And then by applying De Morgan and the distributive law, we find that this is XY prime or X prime Y, and this equal to X exclusive or Y. So now we can conclude that this circuit is an exclusive OR circuit. So the function F equals X exclusive or Y as an example. Another example on the analysis. Now let's look at this circuit, which has three inputs A, B, and C, and it has two outputs, which are F1 and F2. Again, we can call the outputs of the gates T1 the output of this OR gate, T2 the output of this AND gate, and this is simple actually because that's A and B, and this is A and C, and this is B and C. So F2 equals AB or AC or BC, and then F2 prime and T1 we call it T3, and F1 equals T2 or T3. So again we need to be 1 0 1. So A is 1 and B is 0, C is 1, 1 0 1 and 1 0 and 1 1 and 0 1. This will be 0, this will be 1, this will be 0, and that will be 1 here, and this will be 0, and this will be 0, and this will be 0, this will be 0. So we found that F1 is 0 and F2 is 1. So if we again we write down all the variables on this table that we have just the analysis. Now we go to the design of sequential circuit in the next lecture.